Okay, this is quiz review day. The quiz coming up on Wednesday will be, for this lecture, the quiz will be this hour, 1 o'clock, Wednesday in Walker, top floor of Walker. Closed book, all normal. I wrote down what we've covered in this second part of the course, and actually I'm impressed as I write it. So that's chapter 4 on orthogonality, and you're remembering what this is suggesting. Those columns are orthonormal vectors, and then we call that matrix Q, and what's the key? How do we state the fact that those columns are orthonormal in terms of Q? It means that Q transpose Q is the identity. So that's the matrix statement of the property that the columns are orthonormal. The dot products are either 1 or 0. And then we computed the projections onto lines and onto subspaces, and we used that to solve problems AX equal B in the least square sense. When there was no solution, we found the best solution. And then finally, this Gram-Schmidt idea, which takes independent vectors and lines them up, subtracts off the projections of the part you've already done so that the new part is orthogonal, and so it takes a basis to an orthonormal basis. And those calculations involve square roots a lot because you're making things unit vectors, but you should know that step. Okay, for determinants, the big picture is the properties of the determinants. 1 to 3, properties 1, 2, and 3 that define the determinant, and then 4, 5, 6 through 10 were consequences. Then the big formula that has n factorial terms, half of them have plus signs and half minus signs, and then the cofactor formula. So, and which led us to a formula for the inverse. And finally, just so you know what's covered from chapter 3, it's section 6.1 and 2. So that's the basic idea of eigenvalues and eigenvectors, the equation for the eigenvalues, the mechanical step. This is really AX equal lambda x for all n eigenvectors at once, if we have n independent eigenvectors, and then using that to compute powers of a matrix. So you notice the differential equation's not on this list because that's 6.3. That's for the third quiz. Okay. What I usually do for review is to take an old exam and just try to pick out questions that are significant and write them quickly on the board. Shall I proceed that way again? This exam is really old. November 19th, 1984. So that was before the web existed. So not only were the lectures not on the web, nobody even had a web page, my God. Okay, so nevertheless, linear algebra was still as great as ever. So, may I, and that wasn't meant to be a joke. Okay, all right, so let me just take these questions as they come. All right. Okay. So the first question's about projections. It says we're given the line, the vector A is the vector 2, 1, 2, and I want to find the projection matrix P that projects onto the line through A. So my picture is, well, I'm in 3 dimensions, of course. So there's a vector, there's the vector A, 2, 1, 2. Let me draw the whole line through it. And I want to project any vector B onto that line. And I'm looking for the projection matrix. So this The projection matrix is the matrix that I multiply B by to get here. And I guess this first part, this is just part 1A, I'm really asking you, the quick way to answer, to find P is just to remember what the formula is. And we're projecting onto a line, so our formula, our usual formula is A transpose A, inverse A transpose. But now A is just a column, one column matrix, so it'll be just A, so I'll just call it little a transpose, and this is just a number now, 1 by 1, so I can put it in the denominator. So that's really what we want to remember, and using that 2, 1, 2, what will I get? I'm dividing by, what's the length squared of that vector? So what's A transpose A? Looks like 9. And what's the matrix? Well, I'm doing 2, 1, 2 against 2, 1, 2. So it's 1/9 of this matrix. 4, 2, 4, 2, 1, 2, 4, 2, 4. Now the next part asks about eigenvalues. So you see, since we're learning, we know a lot more now, we can make connections between these chapters. So what's the eigenvector? What are the eigenvalues of P? I could ask, what's the rank of P? What's the rank of that matrix? 1. Rank is 1. What's the column space? If I apply P to all vectors, then I fill up the column space. It's combinations of the columns. So what's the column space? Well, it's just this line. The column space is the line through 2, 1, 2. And now what's the eigenvalue? So, since that matrix has rank 1, so tell me the eigenvalues of this matrix. It's a singular matrix, so it certainly has an eigenvalue 0. Actually, the rank is only 1, so that means that there's like going to be a two-dimensional null space. There'll be at least 2. This lambda equals 0 will be repeated twice because I can find 2 independent eigenvectors with lambda equals 0. And then, of course, since it's got 3 eigenvalues, what's the third one? It's 1. How do I know it's 1? Either from the trace, which is 9 over 9, which is 1, or by remembering what is the eigenvector. And actually now it's going to ask for the eigenvector. So what's the eigenvector for that eigenvalue? What's the eigenvector for that eigenvalue? It's the vector that doesn't move, eigenvalue 1, so the vector that doesn't move is A. This A is also the eigenvector with lambda equal 1, because if I apply the projection matrix to A, I get A again. Everybody sees it. If I apply that matrix to A, can I do it in little letters? If I apply that matrix to A, then I have A transpose A canceling A transpose A, and I get A again. So sure enough, PA equals A, and the eigenvalue is 1. Okay, good. Now, actually it asks you further to solve this difference equation. So this is solve UK plus 1 equals P UK, starting from U0 equal 990, and find UK. So what's up? Shall we find U1 first of all? So just to get started. So what is U1? It's PU0, of course. So if I do the projection of this vector onto the line, So this is like my vector B now that I'm projecting onto the line. I get A times A transpose U0 over A transpose A. Well, in one way or another, I just do this multiplication. But maybe this is the easiest way to do it. A transpose, can I remember what A is on this board? 2, 1, 2. So I'm projecting onto the line through there. This is the projection. It's P times the vector U0. So what do I have for A transpose U0? Looks like 18, looks like 27. And A transpose A we figured was 9, so it's 3A. So that this is the x hat, the multiple of A in our formulas. And of course that's 636. So that's U1 computed out directly. That's on the line through A, and it's the closest point to U0, and it's just PU0. Just straightforward multiplication produces that. Okay, now, what's U2? Well, U2 is PU1, I agree. Do I need to compute that again? No, because once I'm already on the line through A, UK will be, I could do the projection k times, but it's enough just to do it once. It's the same. It's the same 636. So this is a case where I could, and actually on the quiz, if you see one of these, which could very well be there, and it could very well be not a projection matrix, then we would use all the eigenvalues and eigenvectors. Let's think for a moment. How do you do those? The point of this small part of a question was that when P is a projection matrix, so that P squared equals P and P cubed equals P, then we don't need to get into the mechanics of knowing all the other eigenvalues and eigenvectors. We just can go directly. But if P was now some other matrix, let's just remember from these very recent lectures how you would proceed. From these very recent lectures, we know that UK, we would expand U0 as a combination of eigenvectors. Let me leave, as a combination of eigenvectors, C1, X1, some multiple of the second eigenvector, some multiple of the third eigenvector, and then A to the K U0 would be C1. So we have to find these numbers here. That's the work, actually. The work is find the eigenvalues, find the eigenvectors, and find the C's, because they all come into the formula. We have So to do this, you can see what you have to compute. You have to compute the eigenvalues, you have to compute the eigenvectors, and then to match U0, you compute the C's, and then you've got it. So it's just that's a formula that shows what pieces we need. And what would actually happen in the case of this projection matrix? If this A is a projection matrix, then a couple of eigenvalues are 0. That's why we just throw those away. The other eigenvalue is a 1, so that we got the same thing every time, C3x3. From the first time, second time, third, all iterations left us with this constant, left us right here at 636. But maybe I'm taking this chance to remind you of what to do for other matrices. Okay, so that's partway through. Okay, the next question in 1984 is fitting a straight line to points, and actually a straight line through the origin. a straight line through the origin. So can I go to question 2? So this is fitting a straight line to these points. I'll just give you the points. At t equal 1, the y is 4. At t equal to 2, y is 5. At t equal to 3, y is 8. So we've got points 1, 2, 3, 4, 5, and 8. And I'm trying to fit a straight line through the origin to these 3 values. Okay, so my equation that I'm allowing myself is just y equal dt. So I have only one unknown, 1 degree of freedom, 1 parameter d. So I'm expecting to end up my matrix. So when I try to fit a straight line that goes through the origin, that's because it goes through the origin, I've lost the constant c here. So I have just should be a quick calculation, and I can write down the 3 equations I'd like to solve if the line went through the points. That's a good start, because that displays the matrix. So can I continue that problem? We would like to solve, so y is dt. So I'd like to solve d times 1 times d equals 4, 2 times d equals 5, and 3 times d equals 8. That would be perfection. If I could find such a d, then the line y equal dt would satisfy all 3 equations, would go through all 3 points, but it doesn't exist. So I have to solve this so that my matrix is now, you can see my matrix. It just has 1 column multiplying a scalar d. And you can see the right-hand side. This is my ax equal b. I don't need 3 equal signs now because I've got vectors. Okay. There's ax equal b, and you take it from there. The best x will come from, so what's the key equation? So here, this is the ax hat equal b equation. Well, ax equal b. And what's the equation for x hat? The best d. So to find the best d, the best x, the equation is a transpose a, the best d, is a transpose times the right-hand side. This is all coming from projection on a line. Our matrix only has 1 column. So a transpose a would be maybe 14 d hat, and a transpose b, I'm getting 4, 10, and 24. Is that right? 4, 10, and 24, so 38. So that tells me the best d hat is 38 over 14. Okay. Fine. All right. So we found the best line, and now here's the next question. What vector did I just project onto what line? See, in this section on least squares, here's the key point. I'm asking you to think of the least squares problem in 2 ways. 2 different pictures, 2 different graphs. One graph is this. This is a graph in the TB plane, TY plane, the line itself. The other picture I'm asking you to think of is like my projection picture. What projection? What vector am I projecting onto what line or what subspace when I do this? So my second picture is a projection picture that sees the whole thing with vectors. Here's my vector, of course, that I'm projecting. I'm projecting that vector B onto the column space of A. Or if you like, it's just a line onto, that's the line. It's just a line, of course. That's what this calculation is doing. This is computing the best D, which is, this is the X hat. So seeing it as a projection means I don't see the projection in this figure, right? In this figure, I'm not projecting those points onto that line or anything of the sort. The projection picture for least squares is in the plane, in the space where B lies, the whole vector B, and the columns of A. And then the X is the best combination that gives the projection. Okay, so that's a chance to tell me that. Okay, I'll go. Okay, now finally in orthogonality there's the Graham-Schmidt idea. So that's problem 2D here. It asks me if I have two vectors, A1 equal 1, 2, 3, and A2 equal 1, 1, 1, find two orthogonal vectors in that plane. So those two vectors give a plane. They give a plane, which is, of course, the column space of the matrix. And I'm looking for an orthogonal basis for that plane. So I'm looking for two orthogonal vectors. And of course, there are lots of, I've got a plane there. If I get one orthogonal pair, I can rotate it. There's not just one answer here. But Graham-Schmidt says, okay, start with the first vector and let that be, and keep that one. And then take the second one orthogonal to this. So Graham-Schmidt says, start with this one, and then make a second vector B. Can I call that second vector B? This is going to be orthogonal to, so perpendicular to A1. If I can, with my chalk, create the key equation. This vector B is going to be this 1, 1, 1. But that 1, 1, 1, 1, 1 is not perpendicular to A1, so I have to subtract off its projection. I have to subtract off the B, the B transpose, yeah, I should say the A1 transpose B over A1 transpose A1. That multiple of A1 I've got to remove. So I just have to compute what that is, and I get a vector B that's orthogonal to A1. It's the original vector minus its projection. Oh, so what is? I mean this to be A2. Yeah. So I'm projecting A2 onto the line through A1. That's the part that I don't want, because that's in the direction I already have. So I subtract off that projection, and I get the part I want, the orthogonal part. Okay, so that's the Graham-Schmidt thing, and we can put numbers in. 1, 1, 1, take away A1 transpose A2 is 6. A1 transpose A1 is 14, multiplying A1. And that gives us the new orthogonal vector B. Because I only asked for orthogonal right now, I don't have to divide by the length, which will involve a square root. Okay. Third question. Third question. All right, I'll move this board up. Third question will probably be about eigenvalues. Okay, 3. This is a 4 by 4 matrix. Its eigenvalues are lambda 1, lambda 2, lambda 3, lambda 4. Question 1. What's the condition on the lambdas so that the matrix is invertible? Okay, so under what conditions on the lambdas will the matrix be invertible? So that's easy. Invertible if, what's the condition on the lambdas? None of them are 0. A 0 eigenvalue would mean something in the null space, would mean a solution to ax equals 0x, but we're invertible, so none of them is 0. The product, however you want to say, no 0 eigenvalues. Good. Okay, what's the determinant of A inverse? The determinant of A inverse. So where's that going to come from? Well, if we knew the eigenvalues of A inverse, we could multiply them together to find the determinant. And we do know the eigenvalues of A inverse. What are they? They're just 1 over lambda 1 times 1 over lambda 2. That's the second eigenvalue, the third eigenvalue, and the fourth. So the product of the 4 eigenvalues of the inverse will give us the determinant of the inverse. Fine. Okay. And what's the trace of A plus I? So what do we know about trace? It's the sum down the diagonal, but we don't know what our matrix is. The trace is also the sum of the eigenvalues, and we do know the eigenvalues of A plus I. So we just add them up. So what's the first eigenvalue of A plus I? When the matrix A has eigenvalues lambda 1, 2, 3, and 4, then the eigenvalues, if I add the identity, that moves all the eigenvalues by 1. So I just add up lambda 1 plus 1, lambda 2 plus 1, and so on. Lambda 3 plus 1, lambda 4 plus 1. So it's lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 plus 4. Right. That movement by the identity moved all the eigenvalues by 1, so it moved the whole trace by 4. So it was the trace of A plus 4 more. Okay. Let's see. We maybe finished this quiz 20 minutes early. Nope. There's another question. Oh, God. Okay. How did this class ever do it? Well, you'll see. You'll be able to do it. Okay. This has got to be a determinant question. All right. More determinants and cofactors and big formula question. Okay. Let me do that. So it's about a matrix, or a whole family of matrices. Here's the 4 by 4 one. The 4 by 4 one is, and all the matrices in this family are tridiagonal with ones. Otherwise, zeros. So that's the pattern, and we've seen this matrix, I guess. Okay, so it's tridiagonal with ones on the diagonal, ones above and ones below, and you see the general formula AN. So I'll use DN for the determinant of AN. Okay. All right, so I'm going to do the first question is, use cofactors to show that dn is something times dn minus 1 plus something times dn minus 2, and find those somethings. Okay. So the fact that it's tridiagonal with these constant diagonals means that there is such a recurrence formula. And so the first question is, find it. Well, what's the recurrence formula? Okay, how does it go? So I'll use cofactors along the first row. So I take that number times its cofactor. So it's 1 times its cofactor. And what is its cofactor? dn minus 1. Right, exactly. The cofactor is this guy uses up row 1 in column 1. So the cofactor is down here. So it's one of those. Okay, that's the first cofactor term. Now the other cofactor term is this guy, which uses up row 1 and column 2. And what's surprising about that? When you use row 1 and column 2, that brings in a minus. There'll be a minus because the cofactor is this determinant times minus 1. The 1, 2 cofactor is that determinant with its sign changed. Okay, so I have to look at that determinant, and I have to remember in my head a sign is going to get changed. Okay, now how do I do that determinant? How do I make that one clear? The neat way to do is, here I see, I'll use cofactors down the first column. Because the first column is all zeros except for that 1. So this 1 is now, and what's its cofactor? Within this 3 by 3, its cofactor will be 2 by 2. And what is it? It's this, right? So that part is all gone. So I'm taking that times its cofactor, then 0 times whatever its cofactor is. So it's really just 1 times, and what's this in the general n by n case? It's dn minus 2. But now, so is this a plus or a sign or a minus sign? It's just a 1 because there's a 1 from there and a 1 from there. And is it a plus or a minus? It's minus, I guess, because it was a minus the first time, and then the second time it's a plus, so it's overall it's a minus. So there's my A and B were 1 and minus 1, those constants. That's the recurrence. Okay. And then it asks you to solve this thing first by writing it as a system. So now I'd like to know the solution. I better know how it starts, right? It starts with D1. What was D1? That's just a 1 by 1 case. So D1 is 1. And what is D2? Just to get us started. And then this would give us D3, D4, and forever. D2 is this 2 by 2 that I'm seeing here. And that determinant is obviously 0. So those little ones will start the recurrence, and then we take off. And then the idea is to write this recurrence as a dn minus 1 is some matrix times the one before, the dn minus 1, dn minus 2. What's the matrix? You see, you remember this step of taking a single second-order equation and by introducing a vector unknown to make it into a first-order system. Okay, so dn is 1 of dn minus 1 minus 1. I think that goes in the first row, right, from the equation above. And the second one is this, is the same as this, so 1 and 0 are fine. So there's the matrix. Okay, so now how do I proceed? We can guess what this examiner's got in his little mind. Well, find the eigenvalues. And actually, it tells us that the 6th power of these eigenvalues turns out to be 1. Well, can we get the equation for the eigenvalues? Let's do it, and let's get a formula for them. Okay. So what are the eigenvalues? I look at the matrix, this determinant, 1 minus lambda and 0 minus lambda, and these guys are still there. I compute that determinant. I get lambda squared minus lambda, and then plus 1. And I set that to 0. Okay. So we're not Fibonacci here. We're not seeing Fibonacci numbers. because we had a sign change there. And it's not clear right away whether this, is it clear? Is this matrix stable or unstable? When we go further and further out, are these D's increasing? Are they going to zero? Are they bouncing around periodically? The answers have to be here. I would like to know how big these lambdas are, right? And the point is probably these, let's see, what's lambda? From the quadratic formula, lambda is 1. I switch the sign of that, plus or minus the square root of 1 minus 4ac. Am I getting a minus 3 there? Over 2. What's up? They're complex. The eigenvalues are 1 plus square root of 3i over 2 and 1 minus square root of 3i over 2. What's the magnitude of lambda? That's the key point for stability. These are two numbers in the complex plane. 1 plus somewhere here, and its complex conjugate there. I want to know how far from the origin are those numbers. What's the magnitude of lambda? And do you see what it is? Do you recognize this, a number like that? Take the real part squared and the imaginary part squared and add. What do you get? So the real part squared is a quarter. The imaginary part squared is 3/4. They add to 1. That's a number that's on the unit circle. That's an e to the I theta. That's a cos theta plus I sine theta. And what's theta? This is like a complex number that's worth knowing. It's not totally obvious, but it's nice. I should see that as cos theta plus I sine theta, and the angle that would do that is 60 degrees, pi over 3. So let me improve my picture. So that's e to the I pi over 6, e pi over 3. This number is e to the I pi over 3 and e to the minus I pi over 3. We'll be doing more complex numbers briefly, but a little more in the next 2 days, next 2 lectures. Anyway, so what's the deal with stability? What do the dn's do? Well, look, if I take the 6th power, I'm around at 1. The problem actually told me this. The 6th power of those eigenvalues brings me around to 1. What does that tell you about the matrix, by the way? Suppose you know, this was a great quiz question, so I should never have just said it, but popped out. Suppose lambda 1 to the 6th and lambda 2 to the 6th are 1, which they are. What does that tell me about a matrix? About my matrix A here? Well, what matrix is connected with lambda 1 to the 6th and lambda 2 to the 6th? It's got to be the matrix A to the 6th. So what is A to the 6th for that matrix? It's got eigenvalues 1 and 1. Because when I take the 6th power, if I take the 6th power, the 6th power of that is 1, and the 6th power of that is 1. The 6th power of this is e to the 2 pi I, that's 1. The 6th power of this is e to the minus 2 pi I, that's 1. So the 6th powers, the 6th power of that matrix has eigenvalues 1 and 1. So what is it? It's the identity. So if I operate this, if I run this thing 6 times, I'm back where I was. The 6th power of that matrix is the identity. Good. Okay, so it'll loop around. It doesn't go to 0. It doesn't blow up. It just periodically goes around with period 6. Okay. Let's just see if there's a... All right. Let's see. Could I also look at at a final exam from 1992. I think that's, yeah, let me do that on this last board. It starts, a lot of the questions in this exam are about a family of matrices. Let me give you the fourth guy in the family has a 1, so it's zeros on the diagonal. But these are going 1, 2, 3, and so on. 1, 2, 3, and so on. But for the 4 by 4 case, I'm stopping at 4. You see the pattern? It's a family of matrices which is growing, and actually the numbers, it's symmetric, right? It's equal to A4 transpose. And we can ask all sorts of questions about its null space, its range, its column space. Find the projection matrix onto the column space of A3, for example, is in here. So A3 is 0, 1, 0, 1, 0, 2, 0, 2, 0. Okay, find the projection matrix onto the column space. By the way, is that matrix singular or invertible? Singular. Why do we know it's singular? I see that column 3 is a multiple of column 1, or we could take its determinant. So it's certainly singular. So the projection matrix will be 3 by 3, but it will project onto the column space. It'll project onto this plane, the column space of A3, and I guess I would find it from the formula A transpose A inverse. I guess I would do all this. There may be a better way. Perhaps, I could think there might be a slightly quicker way, but that would come out pretty fast. Okay, so that's be the projection matrix. Next question. Find the eigenvalues and eigenvectors of that matrix. Okay, there's a 3 by 3 matrix. Oh, yeah, so what are its eigenvalues and eigenvectors? We haven't done any 3 by 3s. Let's do one. I want to find, so how do I find eigenvalues? I take the determinant of A3 minus lambda I. So this is, you just have to, so I'm subtracting lambda from the diagonal, and I have a 1, 1, 0, 0, 2, 2 there, and I just have to find that determinant. Okay, since it's 3 by 3, I'll just go for it. This way gives me minus lambda cubed, and a 0, and a 0. Then in this direction, which has the minus sign, that's a 0, minus 4 lambdas, and minus another lambda, so that's minus 5 lambdas. But that direction goes with a minus sign, so I think it's plus 5 lambda. That looks like the determinant of A3 minus lambda I, so I set it to 0. So what are the eigenvalues? Well, lambda equals 0. Lambda factors out of this times minus lambda squared plus 4. So the eigenvalues are 5. Thanks. Thanks. So the eigenvalues are 0, square root of 5, and minus square root of 5. And I would never write down those 3 eigenvalues without checking the trace, to tell the truth. Because we did a bunch of calculations here, but then I can quickly add up the eigenvalues to get 0, add up the trace to get 0, and feel that well, I guess that wouldn't have caught my error if I'd made it, if that had been a 4, I wouldn't have noticed. The determinant isn't anything greatly useful here, right? Because the determinant is just 0. And so I never would know whether that 5 was right or wrong, but thanks for making it right. Okay. Question 2C, whoever wrote this, probably me, said, this is not difficult. I don't know why I put that in. It asks for the projection matrix onto the column space of A4. How could I have thought that wasn't difficult? It looks extremely difficult. What's the projection matrix onto the column space of A4? I don't know whether this is not difficult. It's just like helpful or insulting. What do you think? What's the column space of A4 here? Well, what's our first question is the matrix singular or invertible? If the answer is invertible, then what's the column space? If this matrix A4 is invertible, so that's my guess. If this problem's easy, it has to be because this matrix is probably invertible, then its column space is R4. Good. The column space is the whole space, and the answer to this easy question is the projection matrix is the identity. It's the 4 by 4 identity matrix if this matrix is invertible. Shall we check invertibility? How would you find its determinant? Can we just take the determinant of that matrix? I could ask you so there are 24 terms. Do we want to write all 24 terms down? Not in the remaining 10 seconds. Better to use cofactors. So I go along row 1. I see 1. The only non-zero is this guy, so I should take that 1 times the cofactor. Now, so I'm down to this determinant. Okay. So now I look at this first column. I see 1 times this. There's the cofactor of the 1. So I'm using up row 1 and column 1 of this 3 by 3 matrix. I'm down to this cofactor. And by the way, those were both plus signs, right? No, they weren't. That was a minus sign. That was a minus. And then that was a plus. And then this. So what's the determinant? 9. Determinant is 9. Determinant of A4 is 9. Okay. Where A3, so my guess is, I'll put that on the final this year, probably the odd-numbered ones are singular and the even-numbered ones are invertible. And I don't know what the determinants are, but I'm betting that they have some nice formula. Okay, so recitations this week will also be quiz review. And then the quiz is Wednesday at 1 o'clock. Thanks.